Ready to have your mind bent a little bit?
I hope so.
Today, we're diving deep into the world of Einstein's theory of relativity.
Sounds exciting.
It is. And we're going right to the source, Einstein's own book, Relativity, the Special and General Theory. We want to make these mind-blowing ideas clear for everyone, even if you've never thought about them before.
You know, what's really cool is that Einstein doesn't just jump into complex equations. He actually starts by challenging something most of us never even question.
What's that?
The absolute truth of geometry. You know, the kind we all learned in school with perfect squares, triangles, and lines.
Euclidean geometry. I have to admit, I never really thought about whether those perfect shapes actually exist perfectly in reality.
Right. That's exactly Einstein's point. He says Euclidean geometry is only true if we can actually draw those perfect shapes using tools like a ruler and compass. It's almost like he's saying geometry, when applied to the real world, should be a part of physics.
Whoa, geometry is physics. It's a pretty big shift.
It is, and it sets the stage for his theory of relativity because it questions the absoluteness of space and time, which are the very foundation of that geometry.
Okay, I'm starting to see the connection. So how does he show that space and time aren't absolute?
He uses this really simple thought experiment with a moving train and lightning strikes.
Okay, I like trains. Tell me more.
Imagine you're on a train and lightning strikes at the front and back of the train at the same time. At least, that's what someone standing still on the platform would see.
I'm picturing it. So what do I, the person on the train, see?
You wouldn't see those lightning strikes as simultaneous at all. And that's a core idea in special relativity. Space and time aren't fixed but change depending on the observer's motion. Something that seems like it's happening at the same time to one person might not be for someone moving at a different speed.
So it's kind of like how our perception of time can feel different depending on if we're super busy or relaxing, but on a much, much grander scale.
You got it. And there's another key piece to this. The speed of light. Einstein says that the speed of light is constant for everyone, no matter how they're moving. This is what leads to that famous equation, EMC.
Gleams he saw, I know that's a big one, but honestly, I'm not sure I completely understand it.
Well, this equation basically tells us that a tiny bit of mass can be converted into a massive amount of energy, which is the whole idea behind the power of stars, nuclear energy, and even black holes. And it sets the speed of light as the ultimate speed limit for anything with mass.
So EMC socket isn't just an equation, it's like a peek into the fundamental rules of how the universe works.
Exactly. But Einstein didn't stop with special relativity. He wanted to understand gravity in this new framework, which led him to general relativity. And that's where things get even wilder.
I'm ready. How did he bring gravity into the picture?
Well, instead of seeing gravity as a force pulling things down, he thought of it as a warping of space-time itself. It's like imagining a bowling ball on a trampoline.
Okay, I can see that. The bowling ball makes a dip in the trampoline, right?
Yes. Now think of that trampoline as space-time. Planets and stars are like those bowling balls, warping the fabric of space-time around them.
So objects aren't really being pulled toward massive objects. They're just following the curves in space-time created by those objects.
You got it. And that goes for light, too.
So light can bend because of gravity.
Yep, and that was actually one of the first big tests of general relativity. During a solar eclipse, astronomers saw that starlight bent around the sun, just as Einstein's theory predicted.
It's incredible to think about.
It is. You know, we started by talking about how Einstein questioned the absoluteness of space and time. Well, he also wondered about the infinity of the universe and explored the possibility of a universe that's finite but unbounded.
I'm not sure I follow. How can something be finite and not have any boundaries?
It's a tough concept to wrap our heads around, but think back to that bowling ball on the trampoline. What if that trampoline was a sphere? Now imagine really tiny creatures living on the surface of that sphere.
Okay, I'm with you.
Their world would be finite because it's just the surface of the sphere, but they could keep walking in any direction without ever hitting an edge. That's kind of like what Einstein was thinking about.
So our universe might be curved like a giant four-dimensional sphere.
Exactly. And to understand this, we have to go beyond the familiar geometry we learned in school and into the realm of non-Euclidean geometries where parallel lines can actually meet and triangles can have angles adding up to more than 180 degrees. It gets pretty wild.
This is blowing my mind. So Einstein's theories gave us a whole new way of thinking about the shape of the universe.
They did. And his ideas about the curvature of space-time led to some pretty amazing predictions, like that strange wobble in Mercury's orbit. Newton's laws couldn't explain it, but Einstein's equations did.
Wow. He basically rewrote the rules of gravity.
He did. And, it's even more amazing because his theories weren't just theoretical. They've been tested and confirmed in the real world time and time again.
It's really incredible. This deep dive has been an incredible journey so far, and we're just getting started.
That's right. We've got a lot more to explore. Welcome back. Last time, we were starting to uncover some really big questions about the universe, like how do we reconcile Einstein's theory of relativity with the strange world of quantum mechanics?
Yeah, it's almost like we have two sets of rules, one for the big stuff and one for the tiny stuff, and they don't always seem to get along.
Exactly. And one of the most mind-blowing places where this conflict becomes really apparent is in black holes.
Black holes, I mean, those are already pretty mind-blowing on their own.
They are, but think about it. Black holes are predicted by general relativity, right? They're these regions of space-time where gravity is so strong that nothing, not even light, can escape. But when we try to figure out what's happening inside a black hole, general relativity kind of breaks down. It says that all the matter in a black hole gets crushed into an infinitely small point, a singularity, and that just doesn't make sense in physics as we understand it.
So it's like the ultimate cosmic trash compactor, squeezing everything down into nothing. That's a little hard to wrap my head around.
It is, and that's where quantum mechanics comes in. At the subatomic level, quantum mechanics says there are limits to how small things can get. So we have this tension between relativity predicting a singularity and quantum mechanics saying, hold on, there's got to be something else going on.
It's those two puzzle pieces, again, fitting perfectly on their own, but clashing when we try to put them together.
Exactly. And this has led to a lot of really interesting theories, like the idea that we need a whole new theory, a quantum theory of gravity, to fully describe what's going on inside a black hole.
Quantum gravity, that sounds pretty intense. What's the basic idea there?
Basically, it's trying to find a way to combine the principles of general relativity and quantum mechanics into one unified theory. Instead of thinking of gravity as a smooth curve in space-time, like in general relativity, some quantum gravity theories suggest that gravity might actually be quantized, meaning it comes in tiny little packets or quanta, just like energy and matter in the quantum world.
So instead of a smooth flowing curve, gravity might be more like a series of tiny bumps or steps.
You got it. Of course, this is all still theoretical, and there are lots of different approaches to figuring out how quantum gravity might work, but it's a really exciting area of research.
Okay, so black holes are like these cosmic laboratories, where we might be able to learn how to combine relativity and quantum mechanics. Are there any other places where this search for a unified theory is happening?
Definitely. Another place is in trying to understand the very beginning of the universe, right after the Big Bang.
The Big Bang. How does quantum gravity fit into that story?
Well, current theories say the universe started as an incredibly hot, dense point, smaller than an atom. And at that scale, both gravity and quantum effects would have been super strong, way beyond what classical physics can explain.
So it's like the ultimate test for a unified theory, describing time when the whole universe was squeezed into a space where both quantum mechanics and intense gravity were at play.
Exactly. If we could understand the physics of that early universe, it could give us incredible insights into how space-time works, where all the matter and energy came from, and maybe even the fundamental laws of physics themselves.
It's amazing how we've gone from wondering about the shape of the universe to pondering the very beginning of time.
It is. And remember we talked about string theory?
Yeah, I've heard of it, but it's always seemed a little out there to me. How does that fit into all of this?
Well, string theory is one attempt to create a theory that includes both quantum mechanics and general relativity. It's a very complex and abstract theory, but one of the cool things is that it naturally includes gravitons, which are theoretical particles that carry the force of gravity. That's something that other quantum theories have struggled with.
So string theory could explain how gravity works at the quantum level.
That's the hope. It also suggests there might be extra spatial dimensions beyond the three we experience, which is a pretty wild idea.
Extra dimensions. So is this all just speculation, or is there any way to test these ideas?
Well, string theory is still in its early stages, and it hasn't been experimentally confirmed yet, but it's a really fascinating area of research, and who knows what we might discover.
This deep dive has really opened my eyes to just how much we still don't know about the universe.
That's the great thing about science. It's a never-ending journey of exploration and discovery.
Back for more mind-bending fun.
Always ready for a deep dive.
Today, we're wrapping up our exploration of Einstein's relativity. And I, for one, am ready to have my concept of time completely shattered.
Time is definitely one of the most intriguing aspects of relativity.
So let's dive in. How does gravity mess with time?
Well, remember how Einstein showed that time isn't absolute, but relative? It turns out gravity plays a huge role in how time actually flows.
Okay, that's a pretty big statement. How so?
Think back to our trusty analogy of the bowling ball on the trampoline, that dip that represents the curvature of space-time. Now, imagine time flowing like a river across that warp surface.
So instead of a straight, even flow, time gets all bent out of shape by those massive objects.
Precisely. And the stronger the gravity, the more warped space-time becomes and the weirder time gets. Essentially, time slows down in stronger gravitational fields.
Hold on. You're telling me that time literally runs slower near massive objects like planets and stars?
Exactly. It might sound like science fiction, but it's a real thing called gravitational time dilation, and it's been measured. Scientists have put super accurate atomic clocks at different heights, and the clocks higher up, further from Earth's gravity, tick just a tiny bit faster than the ones closer to the ground.
Wow, so even that little difference in gravity between, say, the top of a mountain and sea level is enough to make a difference in how time flows.
Yep, it's wild, right? And it has real-world implications too, especially for things like GPS satellites.
GPS. How does relativity affect that?
Well, those satellites are way up in orbit where gravity is weaker, so their clocks run a little faster than clocks on Earth. If we didn't account for that difference, our GPS systems would be way off.
So that little bit of relativity is literally keeping us from getting lost. That's amazing.
It is, and it just shows how powerful and accurate Einstein's theory really is.
We've covered so much in this deep dive. We've explored curved space-time, the possibility of a finite universe, the mysteries of black holes, and even the mind-blowing idea that gravity warps time itself.
It's pretty incredible to think about, right? And it's all thanks to Einstein's curiosity and his willingness to challenge the way we see the world.
He really did revolutionize our understanding of the universe.
He did, but even with all the progress we've made, there's still so much more to explore. The search for a unified theory, one that combines relativity and quantum mechanics, is still ongoing, and who knows what mind-blowing discoveries are waiting for us out there.
I, for one, can't wait to find out. Thanks for joining us on this incredible journey through Einstein's universe. Until next time, keep looking up and keep those minds open to the wonders of the cosmos.